Welcome to the Diligent Automation Programming Excellence Series, Episode 1. Although this series is designed to benefit beginners as well, I won't be spending time explaining common PLC instructions in detail. Let me explain why. My objective is to help you become an industry-ready automation engineer by focusing on practical programming techniques, real-world applications, and engineering best practices. There are already plenty of excellent resources available that explain the basics of PLC instructions. Instead of repeating those fundamentals, this series will concentrate on how to use those instructions effectively to build reliable, maintainable, and professional industrial control programs. Now let's look at this program. This program is running on the Studio 5000 Logix emulator, not on a physical controller. I'm using the emulator simply to demonstrate the behavior of the timer instructions. First, let's look at the timer on delay, TON instruction. The TON instruction starts timing when the rung transitions from false to true. Once the preset time, 5000 milliseconds in this example, is reached, the done DN bit turns on. If the rung becomes false before the timer reaches its preset value, the accumulated time resets to 0. Please note that in the Studio 5000 Logix platform, the timer time base is milliseconds. Next, let's look at the retentive timer on RTO instruction. The RTO instruction accumulates time whenever the rung is true. Unlike the TON instruction, it retains its accumulated value even if the rung becomes false or the controller loses power. The accumulated value continues from where it left off the next time the rung becomes true. To clear the accumulated value and restart the timer, you must execute a reset RES instruction. Finally, let's look at the timer of delay TOF instruction. The TOF instruction keeps its done DN bit on while the rung remains true. When the rung transitions from true to false, the timer starts counting. After the preset time has elapsed, the done DN bit turns off. These are the three fundamental timer instructions available in the Studio 5000 Logix platform. Since the purpose of this series is to teach practical industrial programming techniques rather than PLC fundamentals, we'll use these instructions extensively throughout the series without revisiting their basic operation. Now comes the interesting part. Instead of simply using these built-in instructions, we're going to build our own timer instructions using add-on instructions, AOIs. By creating our own versions of the TON, RTO, and TOF instructions, you'll gain a much deeper understanding of how these timers actually work internally. This approach will help you think beyond simply using an instruction. You'll begin to understand how automation engineers design and implement instruction logic. Once you understand the internal working principles, you'll be able to develop your own reusable function blocks and add-on instructions for real industrial applications. That's a skill that distinguishes an automation engineer from someone who simply writes PLC code. So let's get started. Before we start building the add-on timer instructions, let's first understand this small piece of code. The purpose of this code is to calculate the time slice between two consecutive program scans, or more specifically, between two trigger events. To achieve this, I'm using the GSV, get system value, instruction to read the controller's system timestamp. The destination of the GSV instruction is an array of DINT tags that stores the date and time information. Element 0 represents the year, element 1 represents the month, element 2 represents the day, element 3 represents the hour, element 4 represents the minute, element 5 represents the second, element 6 represents the microseconds. By capturing the timestamp for two consecutive trigger events, I calculate the elapsed time between them in microseconds. I then convert this value into milliseconds. This time slice, expressed in milliseconds, is the value we'll use throughout our add-on timer instructions to implement the timer functionality. If you're a beginner and you don't fully understand this code yet, don't worry. You don't need to understand every detail at this stage. For now, simply remember this. This code calculates the elapsed time between two consecutive trigger events and provides the result in milliseconds. That's all you need to know before we move on to building our own timer instructions. Now let's look at these three add-on instructions. The time slice value that we calculated earlier is mapped as an input to all three add-on instructions. This time slice represents the elapsed time between two consecutive program scans and forms the basis of our timer implementation. Let's begin with the timer on delay, TON, add-on instruction. This add-on instruction is designed to behave exactly like the built-in TON instruction available in Studio 5000. The only difference is that instead of relying on the controller's internal timer, it uses the time slice value that we calculated earlier. Let's understand the logic step by step. The first decision is based on the timer enable input. When timer enable is false, the timer is reset. The accumulator is cleared to 0, ensuring that the timer starts from the beginning the next time the enable signal becomes true. When timer enable becomes true, the EN enable bit is turned on, indicating that the timer is active. The instruction then compares the accumulator with the preset value. As long as the accumulated time is less than the preset time, the instruction adds the latest time slice value to the accumulator. During this period, the TT timer timing bit remains on, indicating that the timer is actively counting. This operation is repeated during every program scan. With each scan, the elapsed time represented by the time slice is added to the accumulator, allowing the timer to accurately measure the total elapsed time. Once the accumulator becomes greater than or equal to the preset value, the timing operation is complete. At this point, the DN done bit is turned on, indicating that the preset time has been reached. So, to summarize, when timer enable is false, the accumulator is reset to 0. When timer enable is true, the timer starts accumulating the time slice value. While the accumulator is less than the preset value, the TT bit remains on. When the accumulator reaches or exceeds the preset value, the DN bit turns on. As you can see, the operating principle is exactly the same as the built-in TON instruction. The difference is that we've implemented the logic ourselves using an add-on instruction. By developing this instruction from scratch, we're not just learning how to use a timer, we're learning how timer instructions are actually designed internally. This understanding will help you create your own reusable add-on instructions and write more robust, maintainable PLC programs. Now that we've understood the TON add-on instruction, let's move on to the retentive timer on RTO add-on instruction. Like our TON add-on instruction, this AOI also uses the time slice value that we calculated earlier. Instead of relying on the controller's internal timer, it accumulates the elapsed time by adding the time slice during each program scan. The main difference between a TON and an RTO lies in how the accumulated value is handled. Let's go through the logic step by step. The instruction first checks the timer enable input. When timer enable becomes true, the EN enable bit is turned on, indicating that the timer is active. The instruction then compares the accumulator with the preset value. As long as the accumulated time is less than the preset value, the latest time slice is added to the accumulator. During this period, the TT timer timing bit remains on, indicating that the timer is actively timing. This operation is repeated during every program scan, allowing the accumulator to increase based on the elapsed scan time. Once the accumulator becomes greater than or equal to the preset value, the DN done bit turns on, indicating that the preset time has been reached. Now comes the key feature of the RTO instruction. When timer enable becomes false, the accumulator is not reset. It retains its current value and waits for the enable signal to become true again. The next time the timer is enabled, timing resumes from the previously accumulated value instead of starting from 0. The accumulated value is cleared only when the reset input becomes true. When the reset input is activated, the instruction immediately resets the accumulator to 0, allowing the timer to start a new timing cycle. So, to summarize, when timer enable is true, the timer accumulates the time slice value. While the accumulator is less than the preset value, the TT bit remains on. When the accumulator reaches or exceeds the preset value, the DN bit turns on. When timer enable becomes false, the accumulated value is retained. The accumulator is cleared only when the reset input is activated. This retentive behavior is what distinguishes the RTO instruction from the TON instruction. It allows the timer to pause when disabled and continue timing from the same accumulated value when it is enabled again. Now let's understand the logic behind our timer off delay TOF add-on instruction. Just like the previous add-on instructions, this AOI also uses the time slice value that we calculated earlier. However, its operating principle is completely different from the TON and RTO instructions. Let's understand the logic step by step. When timer enable becomes true, the instruction immediately resets the accumulator to 0. At the same time, both the EN enable bit and the DN done bit are turned on. This is exactly how a standard TOF instruction behaves. As long as the enable signal remains true, the output remains on and no timing takes place. The timing operation begins only when timer enable changes from true to false. Once the enable signal goes false, the instruction checks whether the accumulator is still less than the preset value. If it is, the latest time slice is added to the accumulator and the TT timer timing bit is turned on, indicating that the off delay timer is currently timing. This process repeats during every program scan, gradually increasing the accumulated time. When the accumulator reaches or exceeds the preset value, the instruction activates an internal reset bit. This internal reset bit turns off both the EN and DN outputs, completing the off-delay timing cycle. So, to summarize, when timer enable is true, the accumulator is reset to 0 and both the EN and DN bits are turned on. No timing occurs while the enable signal remains true. When timer enable becomes false, the timer starts accumulating the time slice value. During the timing period, the TT bit remains on. Once the accumulated time reaches the preset value, the internal reset bit turns off the EN and DN outputs, completing the timer off delay operation. By developing this add-on instruction ourselves, we've recreated the behavior of the built-in TOF instruction using basic ladder logic. More importantly, we've learned the internal logic that makes the instruction work instead of simply treating it as a built-in function. Throughout your career, you'll encounter many built-in instructions, function blocks, and software libraries. Don't limit yourself to using them as black boxes. Always try to understand how they work internally. When you understand the logic behind an instruction, you'll be able to troubleshoot more effectively, design better solutions, and even develop your own reusable add-on instructions for specialized applications. A professional automation engineer doesn't just know how to use an instruction, he or she understands the engineering principles behind it. That mindset is what will help you think beyond the limits of the default instructions provided by the software. Thank you for watching. Thank you for taking the time to watch this episode of the Diligent Automation Programming Excellence series. I sincerely hope this session has helped you gain a deeper understanding of PLC programming and inspired you to think beyond the default instructions available in Studio 5000. If you found this video helpful, like this video, share your thoughts and questions in the comments, share it with fellow automation engineers, subscribe and turn on notifications so you never miss an episode. Coming soon, episode 2, Mastering Tasks in Studio 5000. Program smarter, execute faster, build reliable PLC applications. In the next episode, you'll discover continuous periodic and event tasks explained clearly, how Logic's controllers schedule and execute programs, selecting the right task for the right application, avoiding logical mistakes caused by improper task design, preventing controller performance degradation, engineering best practices for developing efficient, scalable, and maintainable PLC applications. See you in the next episode, Diligent Automation Programming Excellence Series, Engineering Beyond the Default.